Hey guys, welcome back to my YouTube channel. So, today I've come up with a topic from analysis, and yes, that is nuclear magnetic resonance, which is NMR. Now, this NMR is that topic which is very important, very essential, and at the same time, very difficult also to understand. So, today I'm assuring you that after watching this video, you will be able to get an idea about what actually is nuclear magnetic resonance and you will start liking this topic. So, without further ado, let us begin. And also, if you have not subscribed yet to my channel, then please subscribe. And if you like this video, then do press it because it will motivate me and inspire me to make some more. So, let us begin now. What is nuclear magnetic resonance? So, what is nuclear magnetic resonance? Nuclear magnetic resonance is abbreviated as what? NMR. Okay. In this itself, in the name itself will suggest what it includes. That is, it will be including nucleus, it will be including magnetic field, and then there will be resonance. So this technique is basically that technique which is used to elucidate the structure. So if we have been given an unknown compound, then from that unknown compound, if we want to elucidate that what will be the structure of that particular compound, then we can determine it through NMR, that is nuclear magnetic resonance. Now, if an external magnetic field is applied, then NMR will help us to determine the behavior of the nuclei of that molecule when it is subjected to this external magnetic field. So, whenever a molecule will be applied to an external magnetic field, it will have certain orientation. That means the nuclei will spin in response to that magnetic field, that is B0. Okay. Now, when it will spin, so it will have momentum, and as it is spinning, so it will be having angular momentum, right? So, when we have to determine the behavior of the nuclei in response to an external magnetic field, at that time NMR will be helpful, and by that we can determine its structure. Now, it is important for us to know this equation, which is n is equals to 2i plus 1. Now you might be wondering that why we need to know this equation. You will able to know this in a bit. So remember, n is equals to 2i plus 1. Now, what is I and what is n in this? So I is known as nuclear spin. It is also called as spin quantum number. We can also say it as spin quantum number. Okay, I can be written as nuclear spin or spin quantum number. And what is n? N is the number of orientations of nucleus. Now, there could be three values for I, that is nuclear spin or spin quantum number, which could be 0, it could be 1 by 2, or it could be 1. Now, we can determine the value of I from the atom itself. If we will be given a specific atom, then we can determine its spin quantum number. For that, first of all, we need to know the basics. So let us start with the basics first. So say for example, if we have atom X, okay, then atom X will be having its atomic mass, which will be written as A, and it will have atomic number also, which will be written as Z. So you might have studied in 12th standard that what is Z and what is A. You would be knowing this, that Z is what? Z will be the number of protons, right, which is P. And what will be A? It will be the summation of both protons plus neutrons. That is, the number of protons plus number of neutrons, that is P plus N, will be the atomic mass number. Fine. Now, we want to determine the value of I. So, we know that possibly there could be three values of I. It could be either 0, it could be either half, or it could be the 1. So, these are the possibly three values for I. Okay. Now, to determine the value of I, we need to focus at first on this A. What is A? A is atomic mass number. First of all, only focus on A, okay? Don't focus on Z. Now, if A, that is atomic mass number, okay, if that is odd, okay, if A is odd, means it is having odd values. Say I have given here examples like hydrogen, nitrogen, fluorine, phosphorus and carbon. Here just see this A. It is 1, 15, 19, 31 and 13. Means A is what? Odd. In every case it is what? Odd. And as it is odd, when the value of A is odd, I will be half. Then you don't have to observe the Z. If A will be odd, then by default, value of I will be 1 half. That is 0.5. Okay. But in case if A will be even, then come to Z. Then check Z. What should be Z? Z could be either odd or it could be even. We have to check Z. So if Z is odd, means see here in boron, in case of boron, what is A? Even 10, okay. But atomic number is what? It is odd, that is 5. Here also it is 1, here it is 7. But the atomic mass is even. In that case, what will be I? I will be 1. Okay. So that was the another case. But what if Z is even? Means atomic number is also even. See here, mass is even and the atomic number is also even. So when A is even and Z is also even, that means the compound is NMR inactive. That type of atoms won't be able to be elucidated through NMR. Nuclear magnetic resonance will not give us the idea about such type of atoms because their spin quantum number will be 0. So this is how we can determine the spin quantum number or nuclear spin. Okay, this is very important because many times MCQs are also asked for this in JPAT and NIPER, and you can also write this in your theory. So this is very important. Okay, know this. Now let us take the case when I will be half. In that case, we know this equation now that n is equals to 2i plus 1, right? So in that case, when we will substitute I with half, okay, then here you will be getting 1 plus 1 which is equals to 2. So what is n? N is equals to 2. And what was n? N was the number of nuclear orientations. So now when I is half, then possible orientations for nucleus will be 2. Okay. We also know that when this I will be half, when the atomic mass number will be odd, that is in case of 1H and 13C, that is proton 1 and carbon 13, for them I will be 1 by 2. So in that case, total number of nuclear spin will be what? 2. Okay. Now consider this case. So here we have total orientations 2 for nucleus. So when the external magnetic field is applied, which is in this direction, okay, at that time what will happen is the nuclei will have two different spins. One spin will be minus 1 by 2 and the other spin will be plus 1 by 2. Okay, so what is this now? See, when you are applying external magnetic field, at that time what will happen? This will have two possible orientations as per our this equation, okay. So one will be aligned opposite to the magnetic field and other one will be aligned with the magnetic field. So if it is aligned with the magnetic field, okay, so it will require less energy. See, this is the graph for energy. So here energy will be decreased as we will move downwards. So this, when it is aligned towards the magnetic field, it will require less energy, which is in the direction of the magnetic field. But when it is against the magnetic field, it will require more energy and it is aligned opposite to the magnetic field. Fair enough. Now, when we are not applying this external magnetic field, what will happen at that time? The two orientations will have same energy, and when that energy is same, so the delta E, that is change in the energy, would be what? 0, because energy is constant at that time when no external magnetic field is applied. So at that time the change in energy will be what? 0, and so here delta E will be 0. Fine. This was with what? In case of when I was 1 by 2. Okay. Now, here there is some energy difference between these two levels, right? This state is the beta state, this state is the alpha state. Now, according to the Boltzmann distribution, this alpha state is slight in excess as compared to beta state because it is more stable and it is requiring less energy. That's the reason. Now, this is the change in the energy level between these two alpha and beta states, right? Now, if I'm applying an external radiation with a frequency similar to this change in the energy, perpendicular to the magnetic field, then what will happen? There will be the transition from the lower energy state towards the higher energy state. So, if the external radiation is applied with a frequency similar to the change in the energy level perpendicular to the magnetic field, the transition will happen from the lower energy state to the higher energy state, and this transition is known as what? Known as resonance. Got it? So, that is resonance. Now, if we talk about this proton NMR, okay, which is having this case, okay, 1H NMR. In that case, this proton is going to absorb this electromagnetic radiation and the spectrum will be observed, which will be in the form of signal intensity versus chemical shift, which will be written in the form of ppm. Okay. Now say we have applied this frequency f. We know the Planck's equation, which is E is equals to hf. In that case, what is f? F is gamma upon 2 pi into b, which is magnetic field. Now, what is important here to note is that frequency should always be written in megahertz. And what is this gamma? It is gyromagnetic ratio. Gyromagnetic ratio is constant for a specific atom. And from this equation, what we can see that this E, okay, and external magnetic field are directly proportional. So if external magnetic field increases, then energy also increases. Fine. So what is H? H is the Planck's constant. B is external magnetic field and gamma is gyromagnetic ratio. Gyromagnetic ratio is the ratio of the angular momentum upon magnetic momentum. Okay. Now we have to remember the value of gyromagnetic ratio for 13 carbon NMR and proton NMR. The value for gyromagnetic ratio in case of 1H NMR is 267.5 radians per Tesla. And for 13 carbon, it is 67.3 radians per Tesla. Here, it is important to note that proton NMR is having higher gyromagnetic ratio, okay, as compared to carbon NMR. Here it is 267.5 and here it is only 67.3 radians per Tesla. Okay, so it is somewhere around 200 times more as compared to this 13 carbon NMR. Also, this is some basic things which we need to know. 1 Tesla is what? 10 raised to 4 Gauss and 1 Hertz is equal to 1 cycle per second. Okay, this is very important because if we want to go deep in NMR, we need to understand these basic things. Also, note that whenever we talk about magnetic field in NMR, it is always written in Tesla. So you might be given a numerical in which you have been given magnetic field in Gauss. At that time, you need to convert it into Tesla. Okay, and if frequency is given in Hertz, you have to convert it into megahertz. Fine, we will be also saying numerical for the same. So, what will be the frequency? You have to remember this equation, okay? Frequency in megahertz and magnetic field in Tesla is given as frequency is equals to gyromagnetic ratio upon 2 pi into external magnetic field. Fair enough. Now, say in case of 1H NMR, what will be the frequency if such type of numerical is asked to you? Then B is given. The value of external magnetic field is already given to you, which is 1 Tesla, and we have to find frequency. So you have to do simply frequency is equals to what? Gyromagnetic ratio for proton NMR, it is how much? 267.5. So I have replaced it with that. External magnetic field value is given, which is what? 1 Tesla. I have also replaced that. 2 and pi. You are getting 42.6 megahertz. So when one is applying external magnetic field of 1 Tesla, we are getting 42.6 megahertz of frequency. Okay, so this type of numerical questions are generally asked in B.Pharm exams. So practice it well. Practice the same thing with 13 carbon NMR when I am giving external magnetic field of 1 Tesla, and tell me what would be the answer for the same. Okay. This was my small effort to help you guys understand the basics and principles for nuclear magnetic resonance. I hope you have got some clarity, and if you have any doubts, then do let me know in the comment box. I'll be happy to help you out. In the next videos, we will be going deeper in what is NMR. Till then, stay safe and take care.